Hello, I have at this point introduced all the laws of thermodynamics that we will need for this course. We have learnt about the first and second laws, which can be stated mathematically as shown on this slide. We have also seen how the laws of thermodynamics can be combined to give an expression for an infinitesimal change in the internal energy on moving between states. What it is essential to realise in doing this is that the internal energy is a function of state. The integral of this quantity around a closed path is thus equal to 0, and we can thus write the change in internal energy on moving between the two states shown here as a linear combination of the changes in internal energy that occur as we move parallel to the volume axis, which we can calculate by considering the amount of work the system does if the volume changes, and the change in internal energy that occurs as we move parallel to the entropy axis, which we can calculate using the second law of thermodynamics. The final result is that dE is equal to TdS minus PV. In these last few videos, I want to focus on some of the practicalities associated with using thermodynamics to solve problems. In particular, I want to introduce a framework that will allow us to operate at constant temperature and constant pressure, rather than working at conditions where the entropy and volume are fixed. The notion of a thermodynamic potential is going to be critical to this process. We have seen potentials when we discussed Newton's third law. In that video, I explained how we introduce potentials to describe the transfer of momentum between the system and the universe. If you remember, I explained how this makes our life much easier as it allows us to model the coupling between the system and its surroundings without modelling every particle in the universe explicitly in our equations. In other words, we model the effect the universe has on the system in an averaged way. Our aim in this video will be to thus introduce the notion of a thermodynamic potential so that we can pull the same trick within the theory of thermodynamics. Before we get into that, let's just quickly review what we learnt about phase equilibrium and the way that the system interacts with its surroundings. We said that if we have two phases, as shown here, and if these two phases have different values for their pressures, or different values for any intensive quantity for that matter, then they will exchange the conjugate extensive quantity, in this case volume, until the pressures are equal. Thus, in the example shown here, the volume of phase 1 increases, thereby lowering its pressure, and the volume of phase 2 decreases, thereby increasing its pressure. Before introducing our notion of a thermodynamic potential, we need to introduce a reservoir. A system and a reservoir is a special kind of two-phase system in which one of the phases, the reservoir, is enormous. We can use a reservoir to model the interaction between our system and the rest of the universe. Furthermore, because the reservoir is huge, we can safely assume that when extensive quantities are exchanged between the system and the reservoir, the values of the intensive quantities in the reservoir do not change. As such, the values of the intensive quantity in the whole system do not change as heat or work is exchanged between the system and the reservoir. Allow me to explain what that means with an example. Suppose the purple phase, the system, expands slightly here. Work will be done by the system on the reservoir. We know that the amount of work done on the system will be equal to minus PdV. Now, normally, an equal and opposite amount of work would be done on the environment in order to ensure that the total energy of the two phases is conserved. PdV's worth of work would thus be done on the reservoir. The volume of the reservoir would thus change. Herein lies the problem, though. The reservoir is large. In fact, for all intents and purposes, we are going to assume that its volume is infinite. As the volume is infinite, it cannot change. Adding anything to infinity gives us infinity again. We are thus left with a problem. The extra work that would normally be done on the universe is lost because the volume of the reservoir does not change. We thus need to develop a thermodynamic potential that deals with this extra energy. We have to characterize the amount of work that the reservoir would do, as only then can we ensure that energy is conserved throughout our entire two-phase system. To do this, we proceed as follows. Instead of just keeping track of the energy of the system, we keep track of the change in energy plus the change in PV. The second term here is the amount of work the reservoir does when either the pressure of the system or the volume of the system changes. Remember that when the volume of the system changes, the amount of work done on it is equal to minus PdV. In other words, when the system expands, work is done on the universe. The sign of this new dPV quantity is thus positive because we are using it to keep track of the changes that take place in the reservoir. These have the opposite sign to the changes in work that take place in the system. We now proceed as follows. We can use the product rule to write dPV as PdV plus VdP. We then recall that dE equals TdS minus PdV. The minus PdV and the plus PdV terms then cancel, and we are thus left with TdS plus VdP. This sum is the change in a new thermodynamic potential we call the enthalpy. The enthalpy is given the symbol H, and thus an infinitesimal change in this quantity can be written as dH. Enthalpy, like internal energy, entropy, volume, and all the other extensive thermodynamic variables, is a function of state. As such, the change in enthalpy on moving between two states does not depend on the path taken. We could thus always calculate the change in enthalpy by considering a route where we move between our two states at first along a path parallel to the pressure axis, and by then moving along a path parallel to the entropy axis. To calculate the changes in enthalpy along these paths, we perform the definite integrals shown here. This is just another way of understanding the expression we derived on the previous slide that relates an infinitesimal change in the enthalpy to infinitesimal changes in pressure and entropy. Remembering from the theory of partial differential equations that we can always write such infinitesimals as shown here, and equating terms allows us to connect the temperature with the partial derivative of the enthalpy with respect to entropy at constant pressure, and the volume with the partial derivative of the enthalpy with respect to the pressure at constant entropy. An alternative way of thinking about these derivatives is to remember that differentiation is the reverse of integration. If I thus take the integral that gives me the change in enthalpy that I would observe if I change the pressure whilst holding the entropy fixed, and differentiate this with respect to the pressure, I get that the derivative of the enthalpy with respect to the pressure at constant entropy is equal to the volume. Similarly, if I take the equation that gives me the change in enthalpy that I would observe if I change the entropy whilst holding the pressure fixed, and differentiate this with respect to the entropy, I get that the derivative of the enthalpy with respect to the entropy at constant pressure is equal to the temperature. Let's now move on to a second kind of thermodynamic potential. We have thus far assumed that when the entropy of the system increases, the entropy of the reservoir decreases. In other words, we have assumed that entropy is transferred from the system to the reservoir, so that any decrease in the entropy of the system is counterbalanced by an increase in the entropy of the surroundings. What we are now going to do is look at a reservoir whose volume decreases when the system expands. When this reservoir exchanges entropy with the system, however, its temperature will not change. Much as we did with the volume in introducing the enthalpy, we will thus assume that the entropy of the reservoir is to all intents and purposes infinite. And this is the reason that exchanging entropy with it makes no difference to the temperature. Adding or subtracting any finite number from infinity gives infinity. Let's just quickly summarize this all diagrammatically. Here is our purple dot representing the system surrounded by the very large blue reservoir. The entire system is then surrounded by a set of walls that ensure that the whole two-phase system does not exchange matter, heat, or work with its surroundings. The total energy of the system and the environment are thus constant. Let's now suppose that something happens within the system so that heat is exchanged with the reservoir. As we have learnt, if TdS worth of heat is transferred from the environment to the system, then the internal energy of the system will increase by TdS, while the internal energy of the environment will decrease by TdS. This all assumes that the volume of the system in the reservoir remains constant throughout the process, however. Remember, though, that we are assuming that the system is very large and that, as such, the entropy of it does not change when this piddling amount of entropy is transferred into it. We must, therefore, develop a thermodynamic potential that is able to keep track of the total amount of heat and work done within the system, and that also keeps track of the amount of heat that would normally have been absorbed by the reservoir. In other words, in order to ensure that energy is conserved throughout the universe of our system and reservoir, we must keep track of this extra energy, the energy that would normally be absorbed by the reservoir. We must therefore consider the infinitesimal shown at the bottom of this slide, which consists of dE, the change in the internal energy of the system, and dTs, the heat that would normally be absorbed by the reservoir as the entropy of the system increases or decreases. Expanding out the factor of dTs using the product rule, we arrive at the following. We then remember that we could write the dE as TdS minus PV. The factors of plus TdS and minus TdS then cancel, and we arrive at the following infinitesimal, which is the amount a new thermodynamic potential, called the Helmholtz free energy F, changes when the volume or temperature of the system is changed. Once again, this new thermodynamic potential, the Helmholtz free energy, like internal energy, entropy, volume, and all the other extensive thermodynamic variables, is a function of state. As such, the change in Helmholtz free energy that occurs on moving between two states does not depend on the path taken. We can thus always calculate the change in free energy by considering a route where we move between our two states at first along a path parallel to the volume axis, and then by moving along a path parallel to the temperature axis. To calculate the change in free energy along these paths, we perform the definite integral shown here. This is just another way of understanding the expression that we derived on the previous slide that related an infinitesimal change in the Helmholtz free energy to infinitesimal changes in the volume and temperature. Remembering from the theory of partial differential equations that we can always write such infinitesimals as shown here, and equating terms allows us to connect the entropy with the partial derivative of the free energy with respect to temperature at constant volume, and the pressure as the partial derivative of the free energy with respect to the volume at constant temperature. Much as with the enthalpy case, we can understand where these equations come from by considering the fundamental theorem of calculus. Integration is the reverse of differentiation. Hopefully this has given you a flavour of how infinitesimals can be defined by using the properties of reservoirs. There are many more thermodynamic potentials than the two that I have introduced in this video, but if you understand the manipulations that must be introduced in dealing with one of them, then you should be able to deal easily with any new thermodynamic potential. It is simply a matter of changing the letters and hence the thermodynamic variables used. The key thermodynamic potentials are shown here, together with the definitions that are often given to the values of these quantities. If we use the product rules to write out the differentials of all these expressions, we find the following results. If we then substitute the combined version of the first and second laws shown at the top of this slide, we then get to the following expressions for infinitesimal changes in the various thermodynamic potentials. Notice that at the top of this slide I have written out a fuller version of the combined form of the first and second laws than those used in previous videos. I have now introduced a term that describes the work done when atoms are moved into or out of the system, the mu-dn term. This term is necessary here in order to deal with the grand potential shown at the bottom of this slide. I hope you've understood the content of this video and have some understanding of how these expressions are derived. If so, try to see if you could carefully derive one of the results shown on this slide for yourself. Thank you for your attention.